Hello and welcome to NPTEL MOOC on Applied Electromagnetics for Engineers. In this module, we will discuss Maxwell's equations. Maxwell's equations are the basic laws which govern the range of phenomenon associated with electromagnetics from frequencies as low as DC or 0 frequency to frequencies as high as about 10 to the power 15 hertz, that is well beyond the optical range. And it is remarkable that only a few set of equations known as Maxwell's equations supplemented with a few additional equations can describe this entire range of electromagnetic phenomena. There are various ways in which one can approach Maxwell's equations. One can take a purely mathematical way of understanding Maxwell's equations by looking at the equation and then by knowing the vector field and the calculus of vector field that we have discussed in the previous modules, you might already have a picture of Maxwell's equations. If you just look at them, you will be able to interpret them mathematically and physically as well. However, historically Maxwell's equations was not developed as a set of equations. Maxwell did not one particular day come up and then give all these equations along with all the other boundary conditions that we are going to discuss. Historically, the phenomenon of electromagnetics was not even to begin with considered as an electromagnetic phenomenon. People developed notions of electricity first, magnetism, and then developed these two tracks simultaneously or rather parallelly, and then only in the 18th century Faraday managed to bring these two concepts together in order to give you the fact that a changing electric field can induce a change in magnetic field and a changing magnetic field can induce a change in electric field. Based on over 2000 years of development of electromagnetics, Maxwell was finally able to unite the various subjects of electricity, magnetism. The work that was started by Faraday was completed by Maxwell when he introduced the ideas of displacement current. So unfortunately in this course we will not be able to take that historical route. I will give you a very brief and a very simple overview of how this was developed. The actual history is very deep and this is no means a historical lecture or a historical introduction to this subject, but it is important to understand a few basic milestones in the subject, which was the theory of electromagnetics. Then what we will do is we will take the mathematical approach. We will look at the equations at once. We would have defined the corresponding quantities. We will look at the equations, and from the equations we will have a physical picture formed. Later we will consider these Maxwell's equations as a starting point and extend that to the notions of static as well as time varying electric field, with the caveat that we are mostly interested in the time varying fields rather than the static fields. That is because very interesting phenomena happen when fields are varying with respect to time, and it is when fields are varying with respect to time that the true beauty of electromagnetics, in that electricity influencing magnetism, magnetism further influencing electricity, would come into picture. So to give you basic introduction as to what is the historical route in which Maxwell's equations was developed, you need to understand that the notion of electricity and notion of magnetism was not something that was not unknown to people. People had developed over 2000 years ago, especially the Greeks, had understood the idea that if you take a glass rod and rub it with silk and then hold it to matter such as small pieces of wood or small pieces of paper, bits of paper, then this glass rod would attract these bits of paper. Then that was essentially the phenomenon, because Greeks were not really interested in experimental observations, but they were mostly interested in philosophizing. So they nevertheless called this phenomenon as electricity, and then that was the beginning of electricity in one sense. People have observed, so this process of taking this glass rod and rubbing it silk can be extended to many different material combinations, and people who throughout the centuries have actually observed that this is what happens. You take two different materials, not all the materials, but there are a few pairs of materials which you could take, and then when you rub, this process is known as electrification. Then you will be able to attract other bits or small bits of materials by the process of this electrification. The fact that electricity or the electrification could attract bits of matter was not really pursued very much until Benjamin Franklin explored this phenomenon in a slightly more detail, and he actually came up with a nice explanation for this process. He said that when you take this glass rod and then rub silk on it, then there is a imbalance in the amount of charges. So because of this frictional movement, the glass rod will lose some charges while this silk will gain some charges, or it could be vice versa, doesn't really matter. He actually defined two types of charges. He defined positive and negative. So he said that if you rub them, then one particular component, either it could be a glass rod or the silk, which I completely forget which one it is, but one of those materials will end up having excess of positive charges and the other one will have excess of negative charges. At that time, the concept of a proton or an electron was completely unknown. People did not know atomic theory at all, because it was not developed until about a century later on by Dalton. So nevertheless, they understood that there were two kinds of charges, and they also knew this one because when you rub these materials, these combinations, there was a certain place where you bring two different materials which has been rubbed on two different other materials, okay, then sometimes these materials would attract and sometimes these materials would repel. So this was the idea behind saying that like charges would attract and unlike charges would repel. So in other words, you take a positively charged object produced by vigorously rubbing it on a silk rod or some other kind of a thing, and then let's say the glass rod has all the positive charges, and when you bring this positively charged glass with this positively charged material, then they won't attract each other, they will repel each other. Similarly, if I take two silk materials after having rubbed and then try to bring them together, then they would essentially they would resist that motion. So there is a force of attraction and a force of repulsion, which people simplified it with sayings such as like charges attract and like unlike charges repel. Okay. This was all about electricity. This was the state of affairs in about 1800 or so, or slightly before that one, so about 1700 or so, after Franklin did this initial give a nice push to it. The other branch which was developing was magnetism. So people had observed that there are certain naturally occurring materials which was called as lodestone, and this lodestone would attract iron material. So you had a rod made out of an iron, then that iron material or the iron rod would be attracted by this lodestone. Not only that, lodestone would also attract lodestone in different lodestones, and it would also repel different lodestones based on what is the orientation. So people use this effect, which they called as magnetism, use this effect to construct one of the most important instruments that was known to man in navigation, called as compass. Okay. So if you look at old compasses, you would actually see a small needle kind of a thing hanging around, okay, and this needle would always point to the north, and then the opposite end would always point to the south. So this was actually made by a magnet. So this is where the concept of magnetic poles was developed. So every magnet that you would think of would have a north pole and a south pole, and way back in around 1600s or something, I don't remember the exact years, okay, a person postulated that if I take a magnet and then start cutting it into smaller and smaller pieces, I take this big magnet, cut it into pieces, I don't ever isolate a single pole. So I don't ever be able to hold a piece of material and say, okay, this is a north pole material, this is a south pole material. All I always obtain is that if this is a small pole of a magnet this is a small magnet that you have actually carved, this would be the north pole, and there would be a corresponding south pole at the other end. Okay. So in a way, the electric charges and the phenomena of electricity was different than the magnetic phenomenon, except that in magnetism also, like poles would repel and unlike poles would attract. So a pole and a charge were similar, but they were also different, because you could isolate positive charges and negative charges, whereas you could never isolate a positive or a north pole and a south pole of a magnet. So it's a very interesting thing that these two phenomena exhibit similarity but also exhibit differences, and this is how these two subjects parallelly grew. One of the most well-known classics was Theory of Magnetism by Gilbert, where this person, who was a physician to the Queen of England, did lot of experiments on magnetism and condensed all that knowledge into a particularly big book, okay, So you can try to read that book. It's available on archive.org as a free copy. Okay, there is no copyright onto that one. So to sum up, you had a concept of electric charges. There were two types of charges, and like charges would repel, unlike charges would attract. Similarly, you had magnetism on this side. You had two types of poles, north pole and a south pole, but you could not isolate a north pole from a south pole, and like poles would attract, unlike poles would repel. So this was essentially the state of affairs. Until when? Until more quantitative measurements were undertaken by first a person called as Coulomb, okay, Charles Coulomb, and he was a French person. What he did was he constructed delicate balances. They were known as these force torque balances, and then he managed to measure the amount of force that two charges would be either attracted to or repelled by. So he actually did very interesting experiments. We won't have time to go through those experiments, but he did that, and then he showed that you can actually not only calculate, you can not only observe that there is a repulsion or an attraction, okay, attraction or a repulsion, but you could precisely measure this amount of repulsion or an attraction. Okay, this was a very important thing, and he codified it in terms of what is called as Coulomb's law. Coulomb's law actually has two statements, to complete that particular law. It says that two charges would attract or repel, and the magnitude of attraction or repulsion falls off inverse square as the distance between them. Thus, if I have two objects or two charges separated by 10 meter, then the force is actually proportional. The force of attraction, if they happen to be of opposite charges, or the force of repulsion if they happen to be of the same charge type, then that force of attraction was actually inversely proportional to the square of the distance. So 10 meter separation, the force would be proportional to 1 by 100 meters. Okay, so this was 100 meters. So this was very interesting because he could measure this one, and inverse square law was not something that was not unknown to people by then, because a few years ago Newton, or maybe about 50-60 years ago, Newton had actually formulated his even more famous inverse square law, which tells us that there is, in a world or in the universe, objects, masses are always attracting each other, and this attraction force is called as the force of gravitation, and this gravitational force was also proportional to inverse square. So inverse square idea was there, okay, and in fact in much of a sense the inverse square law of Coulomb kind of resembles the inverse square law of Newton. Okay, the second component to Coulomb's law was that the line of the force, which way would the force be attracted to? So if I keep these two charges, imagine that I have kept these two charges here, would this be attracted like this, or would they be going like that, right? So that question was answered by the second component of Coulomb's law, which most people don't really look at that more detail. What Coulomb said is that the line of force of attraction or repulsion would always be along the line that joins these two charges. Okay, so this is my charges and this is the line of the force. Okay, in our modern vector day notation we write Coulomb's law in this way. Okay, suppose I have two charges, call these charges as Q1 and a charge Q2. So the force between these two of attraction or repulsion can be more specified as the force on charge 2 because of the presence of charge 1. Okay, so you imagine that charge 1 was already present, it was fixed to the position, and then you brought in this Q2, and the separation between these two was actually some distance r. Okay, but I know that this point can be given, with respect to some coordinate system. You can actually specify a position vector r1. You can similarly specify another position vector r2. Okay, and then the distance between these two can be specified by another position vector r. Okay, so this force that you actually observe on charge Q2 because of charge Q1, and of course it's a mutual force. Just as Q2 would experience a force of Q1, Q1 would also experience a force on because of Q2, and this was given by some constant k, Q1 Q2 divided by the magnitude of this vector r, and it would be in the direction of the unit vector that joins the two charges. Okay, so it would be along this blue line which is where the force is acting on. So, and along this particular line is where the force is acting on. And if you find out what is the unit vector of this one, of course, what is the vector r? We already know how to obtain the vector r, that is given by r2 minus r1, correct. So, r is equal to r2 minus r1. Therefore, you could go back and rewrite this as constant k q1 q2 divided by r2 minus r1 magnitude cube times r2 minus r1 vector, okay, because r2 minus r1 vector divided by r2 minus r1 magnitude will give you the unit vector. So, this is how you would write in the modern way the force experienced by the charge q2, which is kept at position vector r2 in the space as this particular thing. Now, this constant k can be different in different systems of units. In the modern MKS system or the SI systems, this constant k is given by 1 by 4 pi epsilon 0, where 4 pi is of course what you know, these are the constant, and this is called as rationalized MKS, because the rationalization with respect to 1 by 4 pi is happening in Coulomb's law. Otherwise, this factor of 4 pi would show up in Gauss's law and in all the other different laws. Okay, so Coulomb's law, because we have put in this 4 pi here, this factor 4 pi does not show up in Maxwell's equations when you write those equations in SI units. So, this is what your force law is, and this is what the constant is, where epsilon 0, because I am assuming that the medium here is vacuum, epsilon 0 is called as the permittivity of the vacuum. If I were to replace, or if I were to do the same experiment inside water, then the amount of force that you would observe on the charge q2 because of charge q1 would actually be lesser. The force that you experience, or the force that the charge q2 experiences in a material, is less than the force that is experienced in vacuum, and if you take the ratio of these forces, you end up with another constant called as dielectric or relative dielectric constant, or relative permittivity of the two mediums. Relative is always with respect to vacuum, okay, and this permittivity, because it is a relative measure, is always greater than 1, okay, and the value of permittivity of air, or the relative permittivity of air, is about 1.0008, which is practically close to 1, as is the case of a vacuum. Vacuum of course has a relative permittivity equal to 1, okay, and in SI units this epsilon 0 is given by 8.85 into 10 to the power minus 12 farad per meter. Because this permittivity is an important aspect for defining capacitances, and capacitances are measured in farads, the SI unit is a very practical unit. It will allow you to measure epsilon 0 and specify them in terms of farad per meter, okay. So, this is all that was there known to us through Coulomb, and that was the kind of observation which was available at the time of Coulomb, which was a very important step in electricity. After a few years, people actually developed the notion of current as well, okay, and then they calculated, they found that, you know, if I take a piece of current, okay, and then take one more piece of current in which the current I1 is flowing and then there is another current I2 is flowing, then there will be a force of attraction or there will be a force of repulsion. So, just like this, you know, charges are either attracting themselves or repelling them, so seems to be the case of currents attracting or repelling, okay. But this discovery did not come in this way. It actually came about in a slightly different roundabout manner. People, as I told you, already had this idea of magnetism. So, there was this person called as Ampere who was performing, you know, experiments, and or rather Ørsted who was performing these experiments, and then he actually observed a very interesting thing. He was demonstrating in front of a class, you know, in a classroom, and then he observed that whenever he brought a current carrying wire close to a magnetic compass, right, the moment there was a current, the magnetic field or the magnetic compass got deflected. So, there was some kind of a relationship between current and magnetism, otherwise the current carrying wire would not have deflected this compass, okay. So, there was some kind of an interesting observation that this Ørsted made, and based on this observation later on, okay, and almost kind of independent, not really based on that, but on another continent or another country in France, where this Ampere started to develop his theory, okay, and then he came up with law or with a relationship that tells you what is the force of attraction because of the two current carrying conductors. I am not going to write that one because that's a little complicated expression and I don't want to write that one without introducing you to another effect which people kind of try to understand this Coulomb's law in. Okay. So, let us just keep this idea that current can influence magnetic compasses and then we leave it at that particular point. Okay. Now, if you go back to this force on a charge, right, we have seen that this force is given by some q1 q2 by r square into r hat, right. So, that is the in modern day vector notation, that is how the force can be written. But people were not really happy with this picture, just as they were not happy with the picture of Newton, when Newton said that there are two masses, one may be sun, one may be earth, and if I move earth here by some means that I can think of, then immediately the sun would also carry a force which will move sun as well. So, this phenomenon in which one could change at one particular point a mass m1 and then inflict a force on mass m2 was called, so you have a mass m2 and mass m1, and when you change m1's position, your m2 position would also change because of the force. So, this phenomenon in which you could distantly control the movement or the behavior was called as action at a distance. And people were not very happy with this action at a distance. So, what they said was, well, maybe it does not really work that way. We of course know today that it does not work that way, that if I just take earth and suddenly change earth's position, sun will not really change immediately, there will be some amount of delay, right, and that is what Einstein tells us now, but at that time Einstein was not born. So, people what they did was that they came up with a very interesting notion which has now become very commonplace in physics. They said that whether the second mass m2 is present or not, we do not know, but the mass m1 has a field of influence around it. So, it is like this, I have this pen, okay, this pen, or maybe I have this holder here. Whether I have a pen here or not does not matter, the holder has a certain field of influence, and if I slowly bring in this particular mass here, then these two masses will attract each other. So, since Coulomb's law was essentially the same as Newton's law, people started applying the idea of field of influence, okay, to charges as well. They said that, well, you have a positive charge over here and there is a certain field of influence, and when you bring in this other charge, right, then this other charge would experience a field which would impart a force onto it. So, it is a intermediate step that was created which would have taken the effects from the charge and transferred it to the other charge. This intermediate field of influence is what we now call as field, okay. And we have a first electromagnetic quantity from Coulomb's law, in that you have a charge and there is a field of influence around the charge or simply the field around this charge, and because this is electric phenomena that we are considering, there is an electric field around this charge, okay, and this electric field will take the force or will act on the other charge that is being brought into the field of influence of this first charge and impart a force onto it. How much force is imparted and how is the electric field related to the force? We define electric field as the force per unit charge, okay. So, if you go back to this Coulomb's law over here, you see that you have F2 equal to 1 by 4 pi epsilon naught q1 q2 divided by magnitude of r square, right. So, if I take this force and then divide this one by q2, okay, on both sides, if I divide this one by q2, then q2 will vanish from the right hand side over here. So, this q2 will not be present, and whatever I obtain on the right hand side is what I define as the electric field of the charge q1. So, that is a very interesting way of looking at it. So, this kind of eliminated the problems of action at a distance, because you no longer had this idea that a charge here shaking up would immediately shake the other charge up. What would happen instead is that charge shaking up here, no, not too vigorously, okay, but if I take this charge and very slowly change it up, there is a field of influence or a field, electric field around this charge which would change, and this changing electric field would act like a wave kind of a motion, and then it would impact a force onto the other charge. So, force experienced by any test charge qt would be equal to the electric field at that particular point in the absence of the charge multiplied by the charge magnitude itself. Okay. This is a very interesting phenomenon because the positive charges must have a field of influence which would repel the negative charges, or rather repel the positive charges, whereas a negative charge must have a field of influence which would attract. So you could in fact think of, because the force of attraction and the force of repulsion, you could think of force going away or the field moving away from the positive charge and a field coming towards a negative charge. This is just a convention, you could reverse the convention, but the convention tells you that the field around a positive charge is always diverging away and a field surrounding a negative charge is always converging into it. Okay, this is just a single charge that we are talking about. So we have introduced our first electromagnetic quantity called as electric field. Electric field, we call it field because it is dependent both on the position, right? The field is different at different points, and it is a vector field. The field at this point would be directed here, the field here would be directed along this way for a point charge, right? And if the point charge happens to be a negative charge, then the field at this point would be directed towards the charge in a different way. So the electric field is a vector quantity which further depends on a vector, therefore this is a field vector. And when I change the charge with respect to time, then the field also will change with respect to time, right? So therefore this is a space, or rather in general it's a time varying electric field. Okay. Similarly, we can define magnetic field, and then we will do that one in the next module when we talk of defining the magnetic field, and then bring the concept of electric field and magnetic field together in the form of Maxwell's equation. So until next module, thank you very much.